bunch of them. And it was just the fact that, and I went to the hospital and emergency room and talked to them, and they checked my EKG out. And I said, Doc, when I stand up and do something, it goes away. And he said, okay, step up and down on this stool. So I stepped up and down. It went away. They said, did you have too much coffee? Did you have drugs, weight loss, stress? I said, no, nothing. So some part of my heart just got irritable for some reason, and it just fired. And then
is it still like that, or did it go away?
it went away, but like it was every other one, which was bizarre. That's called bigeminy, when you have every other one. It just got irritable, and I don't know. Occasionally I'll feel a skip beat, but I don't know if it's because I get stressed out or. But just so you know that if you see if you're doing an EKG and you see, I think ACSM says if somebody has like more than 6 in a minute, stop the test, because you don't want it to go into ventricular fibrillation and have the person die. It would be bad. So that's all we're doing with EKG, is just looking at rhythms. And all right, this is the real important stuff. Cardiac output. We talked about this already. Cardiac output is CO or Q. Q dot would be flow. Heart rate times stroke volume. Easy, right? Heart rate times stroke volume. If this is 70 and that's about 70, this is going to be 4,900. 4,900, if I move the decimal place 3 places over, it would be 4.9, or approximately 5 liters a minute. Okay? So it's the amount of blood pumped by your heart per minute. Okay. The way this chapter is organized is they say, since this is a really important thing to talk about, let's talk about regulating heart rate, and then we'll talk about factors that regulate stroke volume. So heart rate, I probably should have, I don't know if this is review for you guys, but you guys know you have a vagus nerve that's slowing your heart rate right now. So parasympathetic nervous system basically acts like a brake. It's saying, hey, slow down, right? So it inhibits the SA node. Parasympathetic inhibits. Increases in heart rate are sympathetic. So you have these cardiac accelerator nerves that when they're activated, they'll stimulate. So in general, slow the heart rate down, and sympathetic is increased. Right? That makes sense. It makes sense. Parasympathetic generally slows things down. Okay. You don't have to remember all this stuff, but it's just trying to show you the SA node and the inputs going to the SA node. And it's showing that we've got sympathetic stimulation and we've got parasympathetic. So parasympathetic is going to slow the heart rate down. Sympathetic is going to speed the heart rate up. And it's just, this is review. It's just showing you kind of inputs. All right, that's enough of that. So, well, let me back up here. If you start exercising, if you guys got up and just started jogging right now, your heart rate increases almost instantaneously. It's like within a second it increases. You go, wow, that's pretty fast. Did you get a lot of sympathetic stimulation? Initially, it's the withdrawal of the parasympathetic. So if this guy's acting like a brake on your heart rate, saying slow down to about 60 beats a minute, and you pull him away, your heart rate just speeds up because you pull the brake away. Right? Does that make sense? Mm-hmm. And then as you exercise longer, then you get more sympathetic stimulation. The sympathetic nerves will help you beat faster, and they'll help your heart contract. So you got both. But withdrawal of parasympathetic, withdrawal of the vagus nerve is the first thing that happens. That's all they say about heart rate. And then they say, let's talk about stroke volume. And stroke volume is really an important variable when we talk about exercise. Some of the terminology that you might not be aware of, end diastolic volume. So here's my heart, and it's pumping, and it goes systole, diastole, systole, diastole. So systole is the contraction, and diastole is the relaxation. So end diastolic volume is at the end of diastole, how much blood is in there right before it's going to beat. So it's relaxed, how much blood is in the heart. And sometimes people refer to it as preload. Your heart is filled up. It's about ready to contract. We'll call it preload. The average aortic pressure, and think about this. My aorta is pretty big, right? It's coming out of my heart. If my heart has to pump the blood through that aorta, so if I had a really small aorta, it would have to pump really hard. If I had a big aorta, you guys know if you blew through a toilet paper tube versus a straw, it's easier to blow through a toilet paper tube, right? You can blow easy. So the average pressure that I have to push against to get that blood out is called afterload. It's called afterload. It's called, it's the pressure that the heart has to pump against. So here's a question for you. If I have aortic stenosis, what is stenosis? Narrowing, right? If I have aortic stenosis, is the afterload going to be higher or lower? No, it's the pressure that I have to pump against. If I have stenosis, my heart has to pump harder to get through, right? So again, stenosis is a narrowing. If I have aortic stenosis, the pressure that I have to pump against is going to be higher. That would be bad. And you think, well, my heart would have to work harder. It has to pump the blood through that small, right? The strength of the contraction, we're going to call it contractility. So my heart's doing this. It's going and diastole and systole, it's squeezing out. And just this is my stroke volume. This is contractility. It's am I doing this or am I doing that, right? And when I'm exercising, the strength of the contraction is going to increase as well as things getting bigger. And so these terms you should be familiar with: end diastolic volume or preload, afterload is the pressure, and then contractility. Okay, so the way the book organizes this, they say, let's talk about this one first, right? So end diastolic volumes on the top. Hopefully you remember the Frank-Starling mechanism. Two physiologists named Frank and Starling. They found that it's basically the more blood you give to the heart, within reason, the more blood you give to the heart, the more it will pump out. So here's my heart pumping. We said it's pumping about 70 times a minute, let's say. Let's say my heart rate's 70. It's pumping about 70 milliliters per beat, right? 70, right? Because we said 70 times 70 is 4,900. So it's pumping about 70 milliliters per beat. One way I can get it to squeeze out 100 or 120 is to fill it more. You know, so if I can somehow get more blood back to my heart, it will squeeze more blood out. That's what the Frank-Starling law says. Greater preload, more end diastolic volume, your heart will pump more out. And I said within reason. What is congestive heart failure? What do you guys know about congestive heart failure? What is it? It's your heart getting enlarged, right? So if I have heart disease, I mean, this isn't athletics heart, because athletes have big hearts. And in the old days, they used to take X-rays, and they called it athlete's heart. They looked at somebody like Galen Rupp and said, "Oh my God, you have athlete's heart. That's bad." Well, they were confusing an athlete's heart with somebody with congestive heart failure. Congestive heart failure is your heart's diseased. It's just not being a very effective pump. There's blood coming back, but it's going, and it's getting bigger and bigger. And you know, there's actin and myosin, and if your heart gets too big, it just can't pump. I don't know if this comes up later. I think it does. But the amount of blood that you pump out is your stroke volume, right? It doesn't do this. Pump 100% out. It pumps about, a good heart will pump about 70% out. So that's called your ejection fraction. Ejection fraction. EF. Just so you know what if you have a normal ejection fraction, you're pumping out, I don't know, 70 or 80% of the blood. If you have congestive heart failure, your heart's big, and it's pumping out maybe 30%. So you go, oh my God, that's pretty bad. Your heart is only pumping out about so when you never want to die of congestive heart failure. That's really bad stuff. So, you know, you'll read stuff where they put pacemakers, or if I had congestive heart failure, the doctor might say, let's put you on diuretics. So why would you put me on diuretics? Get rid of some of that fluid. Because my blood volume, if you can get rid of some of that fluid, then there's not, because remember, blood volume increases blood pressure. So they'll give you diuretics. They might give me some sort of drug that'll help my contraction strength, but it's not so good to have. So the Frank-Starling law says if I give more blood back within reason, not this much blood, because then I'm going to fail. So it's if I give more blood back, how do I get more blood back to my heart? You guys know that I'm getting it from the right side, right? I'm getting blood from the vena cava, right? It's going into my right heart. Gravity is now pulling things down. If I just lie down, that'll help return the blood flow to my heart. Well, but I'm not going to lie down when I exercise. I could do supine exercise. But so there's one way to get more blood to your heart is just to lie down, right? And when you lie down, like right now I'm squeezing 70 milliliters. When I lie down, I'm probably squeezing 100, maybe 120. So it's almost like I'm at maximum exercise when I just lie down. These are the ways that when we're talking about exercise that we're going to be concerned with. So lying down is one way to get the blood back. But if I'm standing and I go for a jog, venoconstriction is a term, vein, constriction, constrict. there's a reflex where I go start running, my veins are going to constrict a little bit. If my veins constrict, veins have valves in them, right? So if my veins constrict, they're going to push the blood back up to my right side of my heart. So just by my veins constricting, that's getting more blood returning to my heart. More blood returns, I can pump it out. Right? So this is a good thing. Skeletal muscle pump. When I jog, again, my muscles are massaging my veins. That's pushing the blood. As long as I've got good valves. If I've got failing valves, then I've got varicose veins. But if I've got good valves and my muscles are massaging, it's going to push the blood back. Right? So that'll increase blood flow to my right heart. Respiratory pump. I start jogging. I'm breathing. The deeper I breathe, you guys know how mechanics of breathing is. When I take inspiration, my intrathoracic pressure goes down, right? So that kind of sucks the blood back into my thorax, right? So a deep breath will help blood get back. So each one of these things helps me get more blood back so that my end-diastolic volume is bigger, and then I can squeeze more blood out because I want my stroke volume to be bigger when I exercise. And this is just shows the one-way valves. So somebody's muscle is massaging the veins, pushing the blood back. That's demonstration of the skeletal muscle pump. Yes.
What was this this word that you said last slide?
Oops.
When you said we normally pump out like 70%.
Oh, ejection fraction.
Ejection fraction.
Ejection fraction is a percent. Ejection fraction. So I think it's just terminology. If somebody has a low ejection fraction, if I said somebody had 30%, that's bad. Normally, I think it's about 70 or 80% that you pump out. It's a normal good heart. You don't want the doctor to tell you have a small ejection fraction. Okay, so there's the skeletal muscle pump. It's just, you guys know we have one-way valves, and that's why I tell you guys, again, straddle the belt when you're done with the exercise test, and you wiggle your toes. That'll help massage those veins and get the blood back so it doesn't pool. Second thing we talked about, again, I'm going to back up. We said end-diastolic volume is one thing, and we know what increases that. Then it says, let's talk about average aortic pressure, or the afterload. So here's average aortic pressure, called the afterload. And again, just as a review, it's the pressure that my heart has to pump against to get the blood out. Just keep on thinking of your aorta as being a toilet paper tube. If it's this big, I still have to develop some pressure to get the blood through there. The narrower my aorta is, the higher the pressure is to pump it out. So it's inversely related, meaning if I take my aorta and I squeeze it down, and you don't do that, your aorta is pretty big, but if I had stenosis, that's going to increase the pressure. That's bad, because increased pressure means my heart has to work harder. It's going to decrease my stroke volume if I squeeze down that exit hole. Does that make sense? So a high afterload, means a narrow aorta would decrease my stroke volume. My heart has to pump harder to get the blood through. And this is kind of weird because we don't really change our aortas. I mean, I'm just using that as an example of like a toilet paper tube versus a garden hose versus a straw. And the smaller it gets, the more pressure. One way to think about it is if you don't want to think about the aorta, you can think about downstream. All my blood vessels downstream. If I constrict everything, my heart's got to pump harder to get the blood out. If I open things up, it's going to reduce the pressure, and I'm going to have a higher stroke volume. So it's almost like saying if my aorta was a toilet paper tube, and if I could make a double toilet paper tube, I would be able to pump more out, which is good. Again, what I want to be able to do is pump more out. I want my stroke volume to be high when I'm exercising because I'm getting blood out. Last thing to talk about, the strength of the contraction. If I increase the strength of the contraction, I'm going to have more blood bleeding, a higher stroke volume. How do I get a stronger contraction? Epinephrine, norepinephrine, right? Those are sympathetic. It's going to squeeze my heart harder. And then direct sympathetic stimulation. So we talked about those sympathetic cardiac accelerator nerves. If I go out and exercise, I'm going to get this, I'm going to get that, I'm going to get a higher stroke volume. So my stroke volume goes from 70 milliliters per beat, maybe to 120 milliliters per beat. So this is important stuff, and I think, let's see if there's a, I don't have the slide. I think there's a slide in the book that, it's like, what factors, I think we did this. Let me see here. Regulation of stroke volume. Let me go back. I want to see something. And that was blood pressure. Stroke volume. Know these. End-diastolic volume, the amount of blood in your heart before contraction, the pressure you have to pump against, and then how strong your heart beats. Those are three factors that will increase or affect stroke volume. And we just talked about them. Okay, so we talked about heart rate is parasympathetic and sympathetic stimulation. Stroke volume is all those things. And then let's put it together. So cardiac output. It's your heart rate, cardiac rate, times stroke volume. We saw that before, so that's easy. Normal cardiac rate, normal heart rate, 70 beats per minute. Normal stroke volume is about 70, something like that. So 70 times 70 is 4,900, or about 5 liters. Does that make sense? You guys, right? This cardiac output stuff. Cardiac output is really important for exercise because we're getting the oxygen that way. Remember, we talked about the respiratory system. We said VO2 max is the maximal rate or maximal ability to take it in. That's your lungs. We said not a big deal. Delivering and extracting. Well, delivering is what we just talked about. So if I have the highest cardiac output here, I probably have the highest VO2 max. So we want a good cardiac output. All right, let's switch gears, talk about the physical characteristics of the blood. And you guys probably know this. You know what plasma and cells are. That's the watery portion. The red blood cells most of the cells are red blood cells. We have a few white blood cells and platelets. But when you think of the blood, think of this. I'm going to spin my blood sample down, and if I spin it down in a centrifuge, all the red blood cells settle down at the bottom. I've got a few little other cells, but mostly red blood cells, and then plasma portion. The hematocrit is just a fraction. So this says a normal hematocrit is about 42%, or when I spin it down, about 42% of my total blood is made up of cells. And okay, that's hematocrit. Why do we care about hematocrit? Well, because this is the stuff that's carrying the oxygen, right? So you say, I wonder if I could somehow increase this. How do you increase red blood cells? Blood doping, EPO. If I increase my blood cells to make it instead of 42%, maybe 50%, you guys agree that I'd have a larger oxygen carrying capacity? What would happen to my viscosity?
It would increase. It
would increase, right? So you go, let me get that hematocrit up to 50%. I'll have more oxygen carrying capacity, but my heart has to work harder because viscosity is now, my heart's having to pump syrup instead of regular blood. So that's bad. You can imagine they could, if I was a cyclist in the Olympics or in Tour de France, they could look at my hematocrit and maybe kind of tell whether I was blood doping or using EPO. What would happen to my hematocrit if I increase this, the watery portion? It goes down. The hematocrit goes down, right? It means the fraction of the cells goes down, not because I remove cells out, but because I put more plasma. One thing that I don't think I mentioned is if I was an untrained person, I think in the very first class we said, I asked the question, that little quiz, I said, what happens to heart rate with exercise, right? Did we do that? And we talked about, okay, so you guys know that when you train, your resting heart rate goes down. So if I said, give me one thing that if I want you to distinguish somebody outside, whether they're trained or untrained, you would probably look at their resting heart rate because everybody knows your resting heart rate goes down with exercise. It's a hallmark training adaptation. Resting heart rate goes down. One other thing that happens when you train is plasma volume goes up. So if you're untrained, and I measured your plasma volume and I measured your hematocrit, it's 42%, after just a few days of exercise, this increases. So you go, why does that increase? Well, because your heart's going, I got to pump this blood. I want to pump a lot of blood out. So let's make more blood so I don't have to pump as much. So it's kind of a negative feedback thing. Your body says, hey, Gary went out and he was untrained. He went out for a jog and he sweat. When you sweat, you're losing plasma volume. And the body says, I don't want to lose plasma volume. So I come back after the exercise, I drink water. Next day I go out again. The body says, holy crap, he's sweating again. Eventually it's going to say, rather than losing this by sweating all the time, why not make this a little bit higher? That way when I go out and exercise, it's less of a disturbance in my homeostasis. So if I had someone out in the hallway and I said, hey, their hematocrit is 35%, you have two choices. One, you say, oh, that person's anemic. They don't have very many red blood cells. Or you could say, he looks like a world-class distance runner. So maybe it's this that's increased. That makes his hematocrit sort of artificially low. Does that make sense to you guys? So there's two ways you can get a low hematocrit. Removing red blood cells, which would be bad, or increasing your plasma volume, which is good, because you've now got more plasma volume to deal with. All right. Hematocrit. All right, that's enough of that. Hemodynamics. So you guys know that if I'm going to pump blood, I've got to talk about pressure, I've got to talk about resistance. Flow is going to be my cardiac output, so let's talk about these things. Pressure. Blood flows from a high to a low pressure. It's proportional to the difference between the mean arterial pressure. So it's basically saying I've got higher pressure at the beginning, lower pressure at the end. The pressure difference, right, is going to cause flow, because the flow goes from a high pressure to a low pressure. That's easy, right? Delta P is just your change in pressure. So when you see this, you say, well, what happens if my blood pressure went from 120 systolic, right? 120 is the squeeze. What if I make it 150? Well, there's a bigger pressure difference, right? I'm going to squeeze more blood out. More blood will flow because I'm more pressure. So the difference in pressure is going to increase. The larger the difference is, the more flow I'm going to get. It's like turning on a garden hose. You know, if I turn on a little bit, it'll trickle. Turn it on high, it's going to be a big pressure difference. This is kind of a cartoon picture just showing my left ventricle is pumping the blood out. The pressure is 100 millimeters of mercury. And it says it's 0 here, but so the pressure difference is 100 minus 0 is 100. So you can imagine if I squeeze harder, and this might be 200, let's say, then it would be a bigger pressure difference, I get more flow. So it's just showing delta P is the pressure difference. The pressure difference increases my flow. What happens to my pressure difference when I exercise? It goes up, right, because I increase my flow. Let's talk about resistance. Resistance is again, there's things that affect resistance. Like the longer the vessel is, the more resistance there is. Our vessels don't change when we exercise. I have vessels that are a certain length, and I go out for a jog. And so really this one isn't, it does affect resistance, but it's not a big thing for exercise. Viscosity is, we said it was like syrup or blood. It's the thickness. Does viscosity change with exercise? Yeah, if you're sweating, you're going to lose some plasma volume. Your blood might get a little thicker, but probably not the biggest deal, right? I mean, I guess if you lost a lot of plasma volume, your blood might get thick, but for the most part, these aren't going to be the big factors. The radius, we talked about the size. Toilet paper tube versus a straw. That's the biggest factor that's going to increase the amount of resistance. And again, I don't want a lot of resistance if I want a lot of blood flow. I want low resistance. And so the formula here says, you know, there's length and there's viscosity, but look at this one. Radius to the 4th power. So you go, holy cow, if I've got a blood vessel and there's blood flowing through there, if I open it up just the radius, if I just double the radius, right, I open up, it's going to increase the amount of flow 16-fold. You go, holy cow, 2 times 2 times 2 times. So just a little increase in the size really affects the flow. Or conversely, if I squeeze down and I half the radius, that my resistance is going to go up. I don't want resistance, right? Unless I'm in shock or something like that. But resistance is going to be, it's inversely related to the stroke volume. And directly proportional to the pressure difference. So we said that, pressure difference, inversely related to the resistance. So when you look at this, you say the amount of blood that I can get flowing, my cardiac output, is going to be related to my blood pressure. So that if my blood pressure goes up, I'm going to get more flow. And resistance. If my resistance goes down, I'm going to get more flow. Does that make sense to you guys? So what happens during exercise? This increases, this decreases, and that increases. That's a good thing. You guys get it? Is it boring?
Oh.
Okay. it's important because it tells us how we increase our cardiac output. You might see, or I don't know if this will make any more sense, if I, instead of saying flow equals change in pressure difference divided by resistance, if I said flow, cardiac output equals, I could put mean arterial pressure divided by total peripheral resistance. It's saying the same thing. I want a high pressure and I want a low resistance if I want my cardiac output to increase. And how do I increase my pressure? I squeeze harder, right? All those things that affected blood pressure. I squeeze harder. How do I decrease my total peripheral resistance? That's all the resistance downstream. I open things up. If I open things up, that's going to decrease resistance. That's exactly what we do. So sources of resistance, mean arterial pressure. When I exercise, my mean arterial pressure is going to, this is going to go up. But this is just telling us not just the size of the aorta, that toilet paper tube. This is looking at everything downstream. And this is review. You guys know arteries, arterioles, veins, venule, you know, the anatomy of the vessels. And you also know that most of the pressure change happens in the arterioles, the resistance vessels. And this next picture, you've seen this in textbooks, every textbook has this. You say, look at the left ventricle, look at the large arteries. The biggest drop is arterioles. The biggest, meaning the blood's going through my vascular system, my arterioles have smooth muscle that can contract and regulate the resistance. If I want to decrease the resistance, my arterioles, the smooth muscle just opens up. So it's the arterioles that are important. It's not really my left ventricle or my aorta. Does that make sense? Arterioles, smooth muscle. Right now, you guys aren't exercising, so you've got only so much blood in your body. You got 5 liters of blood, and so you've got vascular tone. You've got your arterioles and your legs and all over your body are constricted because if they all opened up, you wouldn't have enough blood. Your pressure would crash. You would die. So you've got this sort of vascular tone that keeps your blood pressure where it should be. You start to go jogging outside the park blocks, your body opens things up. That's cool. That's how you get the blood flow to the leg muscles. Yes? Okay, so we're talking about this cardiovascular system because we're really concerned about oxygen, and we know that oxygen, the demand by the muscles, when I exercise, it can go, your VO2 goes up with exercise, right? A lot. So how do I get it? I deliver it. That's this, right? And we said, if I increase my cardiac output, I'm delivering, increasing the amount of oxygen I can deliver. Not only am I increasing my cardiac output with heart rate and stroke volume, but I'm redistributing. That was the second thing that I had on that first slide. I said, it's easy to appreciate when you exercise, your heart rate increases, your stroke volume increases. That's easy. The thing that's also important is I'm taking blood that's going to my spleen, to my kidneys, to my gut, and saying, I'm exercising. Why do I need it there? Let's open things up and redistribute it to the muscle where I need it. So the redistribution is important. Okay. How does cardiac output change with exercise? It's pretty linear, right? But it increases because I increase my heart rate. And when you think about what happens to heart rate, we just said heart rate goes up until it doesn't go up anymore. Same thing with cardiac output. My cardiac output goes up until it reaches max, right? It's linear increase. Cardiac output goes up just like heart rate goes up. It's linear. Heart rate goes up. It can't go past max. You can't. Don't let anybody. I hate when students will say, "Oh, I was above my maximum heart rate." No, your maximum heart rate is as high as it can go. The only way to know it is to go out and exercise as hard as you can and have a heart rate monitor on, or take your pulse accurately and measure it, or do a VO2 max test and you can measure your heart rate max. You guys, we talked about this. 220 minus age was the estimate, right? So if you had to guess, if I had to guess Amanda's max heart rate, I would say 220 minus her age. That's my best guess. I could be right, I could be wrong. There's another formula by a guy named Tanaka, because I told you guys there's different formulas out there, and he came up with 208 minus 0.7 times age. This is much easier to do, 220 minus age. This is harder to do, and it's really, of all the formulas, 220 minus age is the most common one, and it's still got an error of about plus or minus 10 to 12 beats. But it's as good as we can get. People have tried to say, what about 220 minus age minus shoe size? 220 minus age minus something else or plus something. Trying to figure out how can I make that a better formula, and it's really about as good as we can get. So heart rate goes up linearly, right? This says stroke volume. Stroke volume doesn't do what these other guys do. It goes up, here's 10, 20, 30, 40, 50, 60, 70% of max. 10, 20, 30. It goes up to about 40%. It says increases and then plateaus. So this is kind of tricky because when I learned it, it was if we're looking at cardiac output, it goes up linearly. We're looking at heart rate, it goes up linearly. We're looking at stroke volume, and it plateaus. This is kind of the standard thing that everybody learns in exercise phys. It goes up to about 40% and then it plateaus. There is work with athletes that suggest they don't have a plateau, that their stroke volume continues to increase. So it's the safe answer is this, that your heart rate goes up, or your stroke volume goes up to about 40% of your VO2 max and then plateaus. That's the standard answer. But just be aware that there's some work out there showing that it doesn't plateau in highly trained athletes. You guys agree that if this goes up and this goes up, then this is going up because stroke volume times heart rate is cardiac output. So it kind of makes sense.
So you say there's some evidence that stroke volume increases later?
Yeah, it continues to go up, which you would think if we're all untrained people and our stroke volume goes up to about 40% of VO2 max, then you would say, wait a minute, if this is plateauing, but the cardiac output's still increasing, then what's causing the cardiac output to increase? Well, it's mainly heart rate, right? Because ours is plateauing, because this times this is that. And if I said there's an athlete in the hallway and his stroke volume doesn't plateau, you would say, holy cow, that times that is going to be higher. So it makes sense that a highly trained athlete, if there's not a plateau, then they've got an advantage. It means they're increasing their cardiac output throughout the exercise. Which would be a good thing.
But wouldn't it increase less after the plateau? Wouldn't cardiac output increase less? The stroke volume is still the same?
Yeah.
So it'd be curved, it wouldn't be linear.
Yeah. If I show you I think there's like...
I guess it would still be increasing linear, but there would be like a...
I mean, these
like
are
lower
kind of
slant.
even... This cardiac output shows less of an increase, I guess. But those are kind of...
Okay.
I don't like these graphs. They're not that great. But the big picture is linear, plateau.
Okay.
So let me back up. So plateau, oxygen uptake by the muscle increases. All right, so this is saying, you guys realize we're talking about oxygen uptake, and it's two things, delivery and its extraction. This is reminding us that we extract more oxygen, the muscles increase their extraction. It's not just heart rate and stroke volume, it's extraction. And that's the AVO2 difference that we talked about. Yes? Okay.
The what?
The AVO2 difference. The A,
Oh.
there's supposed to be a line.
Oh, okay.
So the arteriovenous oxygen difference, and we're going to come back to this because there's a real important formula that I want you guys to know by heart. It really puts all this stuff together when you look at it. So here's a question, thinking question. There's a guy out in the hallway. He's a world-class athlete, Evan Jager, this 3,000 meter steeplechase. He's got a higher VO2 max than I do. Name two things that make it, two reasons why his VO2 max is higher. And I'll give you some choices. His heart rate, his max heart rate's higher, his max stroke volume's higher, or his maximal extraction of oxygen is higher. Which two of those?
The last two.
The last two.
Yeah,
His stroke volume is huge. His heart rate's probably not that much higher. Well, I'm old, but younger people, if Evan Jager was here, your heart rate's 200, your max heart rate's 200, your max heart rate's 200, his is 200. So the heart rate's not different. It's just your max stroke volume is 120, 120, 120, his is 180. And you can extract, I don't know, 15, I'll just give you a number, 15, 15, 15, he can extract 18. So he can extract more and he can deliver more. Those are the two things. This, even though I don't like these, this reminds me that we're talking about cardiovascular system. We said stroke volume levels off. We said cardiac output kind of goes up linearly. Heart rate kind of goes up linearly. This is the top one is showing us systolic and diastolic blood pressure. So systolic is on the top, diastolic is this line. When we talk about blood pressure, the normal change in systolic, that's the top number, is that it goes up with exercise. So when we do a VO2 max test, if we were going to take blood pressure every couple minutes, we would see 120, 130, 140, 150, 160, 170 until he maxes out. Diastolic doesn't change. You can see it's a straight line. So diastolic doesn't change much at all. At maximal exercise, right now, let's say Carlos has got a blood pressure of 120 over 80. On a max treadmill test, right at max, it might be 190 over 86. So this diastolic didn't change much, but the systolic went up, and that's what that's showing. Does that make sense? And the mean is the middle, is that we talk about mean arterial pressure. The reason I'm saying this, because it's always a test question, you know, what's the normal blood pressure response? Systolic goes up and diastolic hardly changes at all. If it does, it looks like it doesn't change at all. If you had me on the treadmill and my systolic went up to 250, 280, that would be bad. That's just so you guys know that ACSM has reasons for stopping a test. One reason is, you know, the person turns blue. Another reason is the person has irregular heartbeats. Another reason is there's a super duper increase in systolic. Or what if you guys had me on the treadmill and you increased me to the next stage and my blood pressure dropped? That would be bad, right? Because the normal response is for systolic to go up. So either an excessive rise or a drop would be bad. If you guys had me on the treadmill and my diastolic went up a lot, that would be bad. So it's just knowing what the normal response is. Systolic goes up, diastolic doesn't change, can help you, you know, if you're looking at somebody during exercise. I had a slide in my winter, well, what does blood pressure do during resistance exercise? Resistance exercise. Does it increase?
Is there an increase?
Yeah, there's a huge increase. Just think what you're doing. You're doing bench presses. You're contracting all this muscle. It's squeezing everything down. Your heart's going, holy cow, I've got to squeeze through those vessels that are all being squeezed down. Your blood pressures can go up really, really dramatically with resistance exercise. So and especially it goes up even if you guys know what the Valsalva maneuver is? Mm-hmm. It's right. So somebody's doing bench press and they go, oh, holy cow, blood pressure skyrocketing. So you say, oh, that's not good because the person's going to faint. Something's going to happen. They're going to blow up or they're going to poop their pants. If you've got a bad heart, you do that, right? Let's say I've got heart disease and I'm doing a Valsalva maneuver while I'm lifting heavy weights. That's not good. So that's why we tell people to breathe. Okay. The last slide down the bottom, you can't barely see it. It just says, as exercise increases, your AVO2 difference increases. So then we'll talk more about that. Okay, here it is. AVO2 difference. We've just switched from delivery of oxygen to now extraction. So just as a reminder, it's arterial venous oxygen difference. It's the difference between what's arterial, and I said in here, we're always going to say that the blood leaving the aorta, going into the aorta, is going to be 20 mils of oxygen per 100 mils of blood. So 20, 20, 20, 20, 20. No matter who you are, whether you're trained, whether you're untrained, it's just 20. 20 leaving my heart. What gets extracted is the difference, right? So if I'm at rest here, it says my mixed venous, I just pumped 20 mils per 100. Coming back is going to be 15. Well, 20 minus 15, it means I only used 5 because I'm resting. The bottom one says when I'm exercising, maximal exercise, I deliver 20, I extract 15, so only 5 is coming back. So 20 minus 5 is 15. Does that make sense, you guys? This is important for the Fick equation that I'm going to tell you about. The AVO2 difference gets bigger when you exercise. It gets wider. It means you're extracting more. I hope that's making sense.
Yeah, it makes sense.
Okay. So here's rest. It says arterial blood about 20 volumes percent. I wrote it that way because in the old days, instead of saying 20 mils per 100, they would call it volumes percent. And you go, that's a weird way to say it, but that's just the way they did it in the old days, and it kind of makes sense because you guys know what a percentage is. A percentage is how much out of 100, so they would just say 20 volumes percent. It was their shorthand way of saying 20 mils per 100 mils of blood. When I say 20 mils, I'm talking 20 mils of oxygen, 20 milliliters of oxygen per 100 mils of blood, right? Mixed venous, coming back, this is resting. Coming back is 15, so 20 minus 15 is 5. So I only extracted, right? I only extracted 5, right? We just said that in the previous slide. And this is the picture of it. So I'm breathing, getting the oxygen in, and they're taking samples of arterial blood. It says 20 mils per 100. My tissues are extracting some, and what's coming back is 15. So I only extracted 5. It's a picture. You don't have to remember all this stuff, but it's just beating it home. Delivery of oxygen. This is extraction. My muscles are extracting the oxygen. If they extract more, then less is going to be returning to the heart. All right? During maximal exercise, the arterial concentration of oxygen stays the same, so it's still going to be 20, but the mixed venous decreases, so the difference increases. So in this case, I'm delivering 20, I'm extracting some, 11's coming back, so 20 minus 11, I use 9. Yes, yes, yes? AVO2 difference, I'm slamming it home because it's important. So review, heart rate, you guys know. Stroke volume, you guys know. Cardiac output is heart rate times stroke volume. This is saying if I've got a heart rate of 70 beats per minute, a stroke volume of 71.4 mils, then 70 times 71 is about 5,000 milliliters or 5 liters. So that was just, again, giving you guys know this one, my resting heart rate 70, it's just emphasizing that it's about 70 mils per beat for a normal person, normal. It depends on the size of the heart, but it's about 70 is a good number, okay? And 5 is a good number for cardiac output. AVO2 difference, this is a key slide because this is the equation I want you guys to know. So AVO2 difference, we already know, is the difference between the arterial and mixed venous. The PHE equation, this is like the whole, this is the most important thing in the whole chapter. We're interested in VO2 because we talk about VO2 max all the time, you know, the volume of oxygen you can consume during exercise. So VO2, you say, what is VO2? Well, it's the delivery, that's this, cardiac output, and it's the extraction of oxygen, the AVO2 difference. So the cardiac output times the AVO2 difference equals the VO2. Or another way to say it, oxygen uptake. Your oxygen uptake is the product of cardiac output and AVO2 difference. When you think of cardiac output, think delivery, right? It's how much can I deliver? When you think AVO2 difference, think extract. How much can I extract? So I'm going to say this one more time. When I define VO2 max, I say it's your maximal ability to take it in, and we said that's lungs, not a big problem unless you have disease. Delivery, that's this, that's important. And extraction, that's important. So if I can increase my delivery and increase my extraction, I can increase my VO2 max. What do I do with training? With training, I'm going to increase my ability to deliver. I'm going to increase my ability to extract. So aerobic exercise training will increase my VO2 max by doing both of those. If I did this, if I said, I'm going to expand that formula just, this is like a key concept here. My VO2 equals my cardiac output times AVO2 difference, right? AVO2 diff. I'll say diff. Cardiac output is heart rate, right, times stroke volume. So this is my cardiac output. I just said when we train, my VO2 max goes up because this goes up and this goes up. This one doesn't really change much. It's this guy, the stroke volume, that's the important guy. So again, that's me comparing, you with Evan Jager. He's trained, but it's not, his heart rate didn't really do much. His stroke volume did, and then his extraction. So those are maybe another way to say it is if you have to pick heart rate or stroke volume, what separates the world-class athlete from the slug? It's stroke volume. Oof. Big story problem. I want you guys to look at this because it's related to this whole VO2. There's a guy named John. So John's a male, and he's 78 kilograms. That's what that says. All right. He performed a graded exercise test, so he's going to do a VO2 max test. His heart rate, his maximum heart rate's 195 beats per minute. His stroke volume, and then you go, how do you measure stroke volume? Let's just pretend they measured it, right? Because you can't go in there and measure a stroke volume, but let's say they measured it. His stroke volume was 150 milliliters per beat, his maximal. So 195 times 100, let me do this. 195 beats per minute, right? Times, we said 150 milliliters per beat. 150 milliliters per beat, right? What is this? When I multiply this? What's heart rate times stroke volume?
49.
I mean, no, what's the word? I mean, it's cardiac output,
cardiac
right?
output.
Yeah, it's cardiac output. Look at here, I've got beats and beats, right? I cross those out, beats and beats. What am I going to be left with when I do 195 times 150? What units? And what did you give me for the number? You said 195 times 150 is what?
29,250.
29,250?
Yes.
250. Okay. What are the units?
Milliliters a minute.
It's milliliters per minute, right? So you go, wait a minute, we don't express cardiac output in milliliters per minute, so let me move the decimal place. 1, 2, 3 places. 29.25 liters per minute, right?
Yep.
So I'm warning you guys that when I'm doing 150 times 195, I got milliliters, I'm going to get this huge number that's like, you'd say, why, that can't be a cardiac output. It's milliliters, so you got to move the decimal place over 3 places to get liters. I could have done it this way. I could have said this. Watch this. I could have said, let's do 0.150 liters per beat. And I would have gotten 29.25, right? If I just move the decimal place over. Yes?
Mm-hmm.
Okay. So far, I've got this guy. He's got a cardiac output of 29.25 liters per minute. What I want to do, I want to measure his VO2 max. I want to get this answer. Well, VO2 max is his cardiac output times AVO2 difference. So AVO2 difference is, assume that his arterial oxygen concentration was 20 mils. We said 20 mils was going out. Coming back, his mixed venous is 5. So 20 minus, we said 5 is coming back, right? What did he extract? 15.
Yep.
Right? Here's the hard part. This is expressed in 5 milliliters of oxygen per 100 mils of blood. This is 20 milliliters of oxygen per 100 mils of blood. What's going to really be goofy is when I do this, I'm going to get 15 milliliters of oxygen per 100 mils of blood. If I multiply this times this to get my VO2, it's going to be screwy. I'm going to be off. Decimals are going to be off. What I should do is express 15 milliliters of oxygen per liter of blood. So if I make this into a liter, I got to put a 0 there, right? 1,000 mils. Yes? If I add a 0 here, I've got to add a 0 here. It's 150 milliliters per liter. This is a liter, right? Ready? You follow me? So I've got 150 milliliters per liter. This is in milliliters. How do I make it into liters? 150 milliliters is what?
You move the decimal.
Move the decimal place. So it's really, if I do it this way, 0.15 liters of oxygen per liter of blood. Somebody multiply 29.25 times 0.15. 4.4? 4.4 liters per minute. You say, that's his VO2 max. Does it sound like a reasonable number? Well, let's change it to relative and see. How do I change liters per minute to mLs per kg per minute? Milliliters per kilogram per minute. How do I do? 4.4 is 4,400, right? That's milliliters. 4,400 divided by 78. What's 4,400 divided by 78? 56.4. So his VO2 max is 56.4. Does that sound like a reasonable number? Sure. Galen Rupp is 80. Cardiac patient's 15. He's 56. What I'm trying to get you to do is we're putting together his heart rate times his stroke volume times AVO2 difference gives us his VO2 max. It's something you guys are going to have to do, and I know you're going, oh, math, I don't like math. It's summertime, but you have to know heart rate times stroke volume is cardiac output times AVO2 difference. In this case, I gave you the arterial and I gave you the mixed venous, so we calculated the AVO2 difference was 15. But I could easily just give you 15 or 16 or 17 or some number for AVO2 difference. Let me back up here for a second before my alarm goes off. let's see, I've got 10, 15. I want to do this again. This is, I'll post this. I didn't post it yet. Did I post this? Oh, good. All right, good. Because this is what we're talking about. This is PHE equation, which is what I just did. And I give you 3 scenarios. Light exercise, and I just picked, what's light exercise? I said, let's pretend the person's heart rate's 105. And then let's look at moderate exercise. That means either heart rate 120, and then heavy exercise, really heavy. And let's use a 70-kilogram person. So these examples are going to use the same person at 3 different exercise intensities. So check this out. This is the light exercise. I said heart rate, I just made it 105. Stroke volume. How did I get 100 milliliters per beat? I said, well, resting is about 70, so let's make light exercise a little bit more. So I just picked 100, just so that we have a number to deal with. You guys agree that this times this is going to be his cardiac output? Heart rate times stroke volume is his cardiac output, right? Mm-hmm. I picked arterial blood. I said arterial blood coming into the aorta is always going to be 20 mils per 100, so that's always going to be standard. And in this case, here's what I said. I said, he's delivering 20, but he's only doing light exercise, so let's say 12 is coming back. 12 is coming back, is mixed venous. So 20 minus 12 is 8. He's only extracting 8 milliliters because it's light exercise. So these are numbers I'm just kind of making up to illustrate light exercise. When I do this math, if you guys did 105 times 100, right, got his cardiac output, and then you multiplied it by his AVO2 difference, you're going to get 840 milliliters of oxygen per minute. And you go, all right, that's hard to kind of wrap my head around because it's expressed in milliliters per minute. If I wanted to express it relative to his body mass, I would take 840 milliliters divided by 70, and I'd get mLs per kg per minute. I'm going to just do the same thing with a moderate exercise and the same thing with heavy exercise, but I want you to just look at what I did here. Remember I said if I express this in milliliters per beat, and I express this per 100, I get screwy decimals, right? Here, watch what happens here. I'm going to, instead of having, what I want to deal with is beats, and I want to deal with liters, because that's what we deal with. I'm going to change everything. So here's what I'm going to do. I just added a 0 here, right? So if I add a 0 on the bottom to make it liters, 1,000 milliliters is a liter, right? Right here? Mm-hmm. And the next slide says, hey, it's a liter, so 1,000 is a liter. So by adding a 0 there, I got to add a 0 here. Add a 0 there, I got to add a 0 there. Add a 0, right? Mm-hmm. So, and it's hard for me to, when I learned this stuff, I always dealt with 20 mils per 100, 15 mils per 100. Volumes percent kind of stuff. Then you read a textbook nowadays, and they'll say, hey, your normal oxygen concentration is 200 per liter. And it's one of those things where I gotta go, oh yeah, they added a 0. They want to deal in liters. So I'm just showing you how I added a 0, and I changed the denominator to liters. Now it's 200 per liter, 120 per liter. If I do it that way, if I do the arterial venous oxygen difference that way, then I take care of all that decimal stuff that's going to go screwy on me. I'll end up in liters, and that's what I want. Stroke volume, I changed. 100 milliliters is 0.1 liters. So now when I do all the math that way, I get 0.840 liters per minute. When I convert it to mLs per kg per minute, I get 12. And you say, okay, this is light exercise. When you guys are resting, what's your VO2? When you're resting, your VO2 is 3.5, right? Because that's 1 met. And so this guy is now, I don't know, 3.5, 3.5 is 7. He's a little over 3 mets. He's doing some light exercise, but it's not really heavy exercise because his heart rate's only 105, but that's how we got his VO2. The light exercise is the hard one to think about, so let me do the moderate, and then I'll do that. And it's going to go off in 6 seconds. You guys want to take a break now? Because you're looking at numbers. 10 minutes. And I'll leave this up here because this is really important stuff, even though it doesn't seem like it's fun.